Alright, so what we need to cover in this video is how we find the pH of acidic solutions that are not necessarily all strong acids and strong bases when you're just given the hydrogen ion concentration. So we're going to go back to equilibrium and ice tables and solving for X's primarily. So we think about acid-base equilibria, okay, and life's going to get a little bit more interesting, both this chapter and chapter 15. You have to take a step back and think about the chemistry, meaning you have to focus on the solution components and the reactions that are taking place. So this is kind of where you have to really take a minute to kind of think through what you're solving for, how you're solving for it, and what's going to influence. For example, if you have hydrochloric acid solution, you have to think of the fact that the solution contains hydrogen ion and chloride ions, not hydrochloric acid molecules, because it's a strong acid, okay? So what you have to do is determine which components are significant and which can be ignored, and that's going to drive what's going to happen in that solution. Now, we will keep defining sometimes what's called this major species. Major species are the solution components present in relatively large amounts. So, for example, in a 1 molar hydrochloric acid solution, which we saw in one of the last videos was like a 0 on the pH scale, the major species of hydrogen ion, chloride, and water. It's very acidic, so hydroxide is only going to be present in very tiny amounts. So that's the kind of thinking of chemistry that I'm talking about. Now, for a strong acid, okay, and again, you're going to have to double check on these slides because there's going to be, I think there's a mix of things you have to write down and things that I already gave for you. But for strong acids, they completely form ions, so you don't use the Ka value or an ice chart. Okay, you solve them exactly like we did last section. So to find the pH of a 0.1 molar nitric acid solution, it's a strong acid. Now you'll see this to always write out the important or major species. It's kind of like the known and the unknown in terms of an organization. But in this solution, your major species present are hydrogen ion, nitrate, and water. Okay, now we know water will exist a little bit in the autoionization of hydrogen ion and hydroxide ion, but it's only a very small amount, so in essence it can be ignored. So for nitric acid, we can go right to our pH equation and find out that with a 0.1 molar solution, we end up with a pH of 1.00, 2 sig figs, 2 decimal places, and that's it. Okay, those are the easy ones when it's just strong acids. Now, also, one thing that you got to look out here is for this particular solution, look on page 666, you have a 1.0 times 10 to the negative 10th molar hydrochloric acid solution. Now, hydrochloric acid will dissociate, completely dissociate into hydrogen and chlorine. Water will also autoionize. Now, water's contribution to hydrogen ion is larger. Now, you may say, well, how the heck am I supposed to know that? Well, remember, for the Kw, okay, is always equal to 1.0 times 10 to the negative 14th, but that's not what we're comparing it to. Where we get Kw is in a neutral solution, the concentration of both hydrogen and hydroxide is 1.0 times 10 to the negative 7th. It's going to be a bad 7, but negative 7 is greater than negative 10, so that means that water's contribution is going to trump it, so hydrochloric acids can be ignored in this situation. So our pH, we use water's contribution, and it's going to be 7.00. Okay, that's kind of tricky, but remember, when you're comparing it, people will get confused and try to compare it to Kw, which you're not. You're comparing it to what the hydrogen ion concentration would be. Okay, weak acids are different. All right, so for weak acids, you got to write down your major species, decide which one's going to provide your hydrogen ions. We're going back to the ice chart, just like we did in chapter 13. We're going to put equilibrium values in Ka. Now we're going to check the validity of the assumption, and I kind of skipped through this a little bit, but essentially what has to happen is that X has to be less than 5% of the initial concentration. I'm going to show you how to do that because it won't necessarily always work. Then our last step is to find the pH. With chapter 13, it was always finding the concentrations at equilibrium. Now it's actually using the values to find the pH of the solution. Okay, so let's find the pH of a solution, 1 molar solution of hydrofluoric acid. Ka value is 7.2 times 10 to the negative 4th. For your book problems, just FYI, there's a chart, I'm not sure what page it is in the chapter, that lists several of the Ka values. So refer back to that chart. Remind me in class and I'll tell you which page it's on. Okay, so the major species are hydrofluoric acid and water. Now for hydrofluoric, Ka is 7.2 times 10 to the negative 14th. way less than hydrogen ions contribution from Kw. So differences to the Ka and the Kw value. More importantly, again, hydrogen ions concentration times 10 to the negative 7th in order to get that one, okay? Now, we set up our ice table, okay, and we got to solve for x. Now, here is the math to solve for x, same way we did last semester, or last chapter rather. Again, what we're going to skip to make the math easier is this section right here, because since Ka is times 10 to the negative 4th, it's 1,000 times smaller than 1, we're going to ignore that, and we're going to get our x value of equal to 0.027 when we solve for x. Now, to check the assumption, and this is what I haven't done a ton of, in order to check the assumption, you have to make sure that the x you ignored is essentially less than 5% of whatever you were subtracting it from. Okay, so if we look at this one, this is the x value that I just solved for, which is 0.027. This happens to be the concentration of the original acid, or whatever we were subtracting it from, because remember, what we crossed off was 1.00 minus x. Okay, we do that math, it comes out to less than 5%. That means the assumption is good. It's not always going to come out this way. Some of our together problems won't, but that's how you check the assumption. It's pretty straightforward. Now we got to find the pH value. So you take that x value, because it was your hydrogen ion concentration, you get a pH of 1.57, no unit, because we're dealing with pH. Okay. All right, another example, you can find this on page 669 in your textbook. You've got a pH of 0.1 solution of this acid that has a Ka value of 3.5 times 10 to the negative 8th. Again, this acid will provide more hydrogen than water, hydrogen ion here, because we're comparing it to that Kw value. Okay, so we got a plug and chug here on our ice table. We solve for x. X comes out to be 5.9 times 10 to the negative 5th for molarity. And if you come back here, all right, so if we come back here, if you remember, when we were solving for x, that x value was the hydrogen ion concentration. So that's why we can go back and solve for it. Okay, so we solve for x. X is 5.9. We check our assumption. It's way less than 5%. So remember, all we're doing is plugging in the x value, and this is whatever we subtracted the x from, making sure that it truly could have been ignored. We go back into our pH equation. We plug that in. We get a pH of 4.23. Now, with a mixture of acids, you always want to deal with the strongest acid first. And if it's one of them is a strong acid, well, that dictates it. And second of all, if it is two weak acids, you use the Ka value to figure that out. Then you use your equilibrium values, there you go, to begin your weaker acid. Okay, so again, find the pH of a mixture of hydrocyanic and nitrous acid. Well, we're going to deal with the nitrous acid because it has the highest Ka value. So we got to find the hydrogen ion concentration of just the nitrous acid, which is going to be that x value right there. Ka is still more than 1,000 times smaller than x, so we're going to go ahead and get rid of that x value here. Right? We solve, and the first x value is going to be 0.045 molar. Then what we have to do, and here's where the mixture comes in, you take that 0.045 and you plug it in as the initial concentration for the hydrogen ion for the second component. So this is part 2, which we do exactly the same, or the second acid or the weaker acid, except we take that original x value and we plug it right in there, and then we do the same thing in order to solve for these. Okay, but on these, if we go ahead and ignore our x's, okay, that's where the little squiggly line comes in, we get an x value of 1.4 times 10 to the negative 8th. Apparently that's really important. So then what we do to find it is we add both of them together, and I know this is really small, but remember we had to add the values from both acids. This was acid number 1 and number 2. Okay, so it still just ends up being the first one, but yes, you still have to do the math. So it's got a pH value of 1.35. Okay, and if you also went back and found the cyanide ion at equilibrium, you go back and you use the x value from the second ice chart, or you can solve for it again what we just did on that last value. Okay? All right, now the last topic we're going to talk about is percent dissociation or percent ionization, or in other words, how much dissociates based on the initial concentration that we had. For a weak acid, the percent dissociation will increase as the molarity decreases. The solution becomes more dilute, and there's more essentially, I always think of it as room for it to move around. So the dilution will shift equilibrium to the side with the greater number of particles, just like we saw with gases and Le Chatelier's principle. If you dilute it, it's just like increasing the volume, it's going to have more room to move, so it'll go to the side with more particles. And this is just showing you, more concentrated, more dilute, what's going to happen to these different acid concentration versus percent dissociation, etc. And some of them are going to be directly or indirectly related. Okay, so let's calculate percent dissociation. This is example 1410 in your textbook for 1 molar acetic acid. So first we got to find they give us the Ka value. Okay, we got to solve for x, just like we've been doing. Okay, solve for x. We've got 4.2 times 10 to the negative third. And on any of these where I'm just not checking the assumption, it works. Okay, you should try to get in the habit to make sure that you check the 5% rule, but whenever you see me not checking it, I know it works out, but just know in this unit, and I'll try to point you in the right direction of the ones that don't, it may not always work out, and that's when you're going to have to use the quadratic formula. Okay, but anyway, here's our amount dissociated over the initial concentration. So the amount dissociated is essentially what we found for our x value. 1.00 is the original concentration that they gave us. So times 100, we find that only 0.42% of it dissociates. So when we talk about weak acids and weak electrolytes, it's really a very small amount compared to those strong electrolytes and those strong acids. Okay, here's another 0.100 molar acetic acid. This is to kind of drive home the point. The ice table would have looked exactly the same as with the last one. So it would be 1.3 times 10 to the negative third. And again, it's driving home that point that we had a much smaller value for 1 molar, but when we dilute it to 0.1 molar, not that it goes up, tens of percentages, but it does go up to 1.3%, which is still larger than what it was with the 1 molar concentration. Okay, so that's percent dissociation, which we just do. It's kind of like percent yield, meaning you do it kind of at the end of when you do one of these problems. You also can work backwards to figure out Ka. So in a 0.2 molar solution of a weak acid, 2.5% of the acid is dissociated. Find the Ka value. So if you work backwards, here is what I'm looking for, is the amount dissociated. Here's my percent dissociation and my original amount. So I solve x of 0.0050 molar. Okay, and then I can work backwards from an ice table to figure out here would be my generic acid with the original concentration. Here is still that original, the x is still the same, except what we're going to do is we're going to go ahead and plug our values in for x. And we're not going to cross them off this time because we don't have to. Plus, if you look at it, 0.005 is not all that much smaller. So since it's not making our algebra more algebra easier, we are going to go ahead and leave it, and we can solve for a Ka value of this acid of 1.3 times 10 to the negative fourth. Okay, so I hope that helps, and we'll do bases in the next